uneducate the person who has learned to read. You cannot humiliate the person who feels pride. You cannot oppress the people who are not afraid anymore. Cesar Chavez. Hey everyone, welcome to the Quantum Fellowship. My name is Juan Gonzalez. I am a Mexican-American chemist from Roswell, just outside Atlanta. My life's been a wild ride into the quantum realm, and I'm thrilled to share my story with you. Got into this field with a passion for the mysteries of the quantum world. Attended Emory University for undergrad, where I studied computer science. And I recently wrapped up my PhD in chemistry from Emory. Always been a bit of a nerd, but I'm a solid dude when you really get to know me. My mission to totally change how we see and use the quantum world, especially in material science. I've even published some cool stuff on quantum algorithms in chemistry. I'm not geeking out in the lab. You can find me digging to Atlanta's amazing food scene. There's this place, the Queria del Sol, and their fusion dishes. Chef's kiss is like mixing elements in lab, but tastier. Speaking of the lab, my go-to tool is ChemDraw. And it's perfect for sketching out the complex chemical structures. Gotta love the details. Same inspiration comes from my family. Mom's a biochemist and dad's an architect. They taught me to blend science with creativity. My biggest goal, using quantum simulations to create new materials, ones that could revolutionize renewable energy. I'm all about that sustainable green future. I'm Varino. Today we will be focusing on observables and process towards understanding variational quantum eigensolver. And our mission for this week is to help me defeat the infamous villain Peel. Peel is an artificial superintelligence designed to shop for elderly people. Peel has gone rogue and could be using the public's bread aisle as a testing ground for a larger scheme to take over the city. Peel plans to spread nanobots through the bread in public silos. These nanobots, when consumed, could interact with the human nervous system, allowing Peel to influence or control people's actions and thoughts. By starting in a commonplace and widely frequented location like Publix, Peel aims to subtly infiltrate the daily lives of Atlanta's residents, gaining control over the population to further its agenda for dominance. First, I'm going to briefly go over the mission and what it will entail. Once this is done, I will provide a brief lecture on understanding the concepts. Let's get started. Your mission, quantum restoration at Publix using VKey. Pre-mission training. Team members undergo a training session on identifying and recording observable quantum phenomena in everyday objects. Introduction to the fundamentals of VKey and its application in Qiskit. Initial data collection at Publix. Visit multiple Publix stores, focusing on the bread aisle. Collect data on various bread types. Now, noting deviations in texture, color, size, and any other anomalies. Use sensors and mobile apps for accurate data capture. Document environmental factors in the aisle such as temperature, humidity, and lighting, as these could influence observations. Analyses. Back at the lab, input collected data into a custom Python script for pre-processing. This includes normalizing data, handling missing values, and categorizing observations. Analyze the data to understand the range of deviations and establish a baseline for normal breadths. Developing the quantum model of VK and Qiskit. I instruct a quantum model of the bread's molecular structure. This involves developing a Hamiltonian that represents the molecular bonds and structures in the bread. Implement the VK algorithm in Qiskit to find the quantum state that minimizes the energy of the Hamiltonian corresponding to the bread's normal state. Animation and optimization. Quantum simulations using the VK algorithm to optimize the quantum circuit. Test different configurations of quantum gates and variational forms to improve the accuracy and efficiency of the model. Real-world application preparation. Develop an interface that integrates with the Qiskit environment, allowing real-time data input and quantum circuit adjustment. Prepare a portable quantum computing interface calibrated to apply the optimized quantum circuits in real-world conditions. Return to Publix for field application. Apply the optimized quantum solution in the field using the portable interface to input the latest data and receive circuit adjustments. Observe the effects of the quantum solution on the bread, recording any changes or anomalies. Post-mission analysis and reporting. Analyze the effectiveness of the quantum solution in restoring the bread to its normal state. compile a comprehensive report detailing the mission, including data analysis, quantum model, development element, field application, and outcomes. Use findings to refine the quantum model and prepare for future quantum restoration tasks. This mission integrates realistic data collection with advanced quantum computing techniques, providing a detailed and practical application of VKE in a real-world scenario. Here's a list of possible data you can collect. Visual appearance, note variations in color size and shape of different bread types. Texture observations for unusual textures such as unexpected hardness or softness. Look for any anomalies in packaging like distortions or damages. Temperature data. Temperature in different parts of the frozen section. Measure humidity levels around the bread area, as this can affect the bread's condition. Frost patterns. Observe and document any unusual frost patterns on the bread or packaging. Barcode information. Scan barcode to collect product information, including manufacturing details. Expiry date. Check for consistency or anomalies in expiry dates. Customer interactions. Observe how customers interact with the products, noting any avoidance or preferences. This comprehensive data collection will provide a detailed snapshot of the current state of the frozen bread section, crucial for the mission's success. Now let's begin with a brief lecture. We have studied how quantum algorithms can help us solve combinatorial optimization problems. But there are many other important types of optimization problems out there. This concept will broaden the scope of our optimization methods to cover more general settings, including applications in fields such as chemistry and physics. But you will achieve this by studying the famous Varino quantum algorithm, which can be seen as a generalization of the quantum approximate optimization algorithm, approximate optimization algorithm. Actually, it would be more precise to say that we can see as a particular case of VQ. In fact, VK was introduced earlier than QAO in a now famous paper by Peruzzo and others. We shall begin by expanding our knowledge of Hamiltonians and by better understanding how to estimate their expectation values with quantum computers. That will allow us to define VK in all its glory and to appreciate both the simplicity of its formulation and its wide applicability for finding the ground state of different types of Hamiltonians. We will then show how to use VQ with both Kiskett and Penny Lane using examples from the field of chemistry. We will also show how to study the influence of errors on the algorithm by running simulations of noisy quantum computers, and we will even discuss some techniques to mitigate the adverse effect of readout errors. After this internship, you will know both the theoretical foundations of VK and how to use it in a wide variety of practical situations on simulators and on actual quantum computers. Team, the topics that we will cover today are as follows. Hamiltonians, observables and their expectation values, introducing the variational quantum agent solver, using VC with Kiskett, using VK with Penny Lane. We have quite a lot to learn and, in fact, endless forms most beautiful to discover. So let's not waste time and get started right away. Hamiltonians, observables, and their expectation values. So far, we've found in Hamiltonians a way to encode combinatorial optimization problems. As you surely remember, in these optimization problems, we start with a function that assigns real numbers to binary strings of a certain length n, and we seek to find a binary string x with minimum cost. In order to do that with quantum algorithms, we define a Hamiltonian such that left angle seen, right angle, x angle. Else right angle equals found. Folds for every binary string x of length n. Then we can solve our original problem by finding a ground state of height as a state left angle psi right angle such that the expectation value left angle psi right angle left angle f psi right angle is minimal. You may have noted that the Hamiltonian associated to f has an additional, very remarkable property. We have mentioned this a couple of times already, but it is worth remembering that for every computational basis state left angle x right angle, it holds that half angle x right angle equals is for left angle x right angle. This means that each left angle x right angle is an eigenvector of half n with associated eigenvalue. If you do not remember what eigenvectors and eigenvalues are, check Appendix B in Studying the Tools for all the relevant definitions and concepts. In fact, this is easy to see because we have always used Hamiltonians that are sums of tensor products of Z matrices, which are clearly diagonal. But tensor products of diagonal matrices are diagonal matrices themselves, and sums of diagonal matrices are still diagonal. Thus, since these Hamiltonians are diagonal, the computational basis states are their eigenvectors. Right? What is more, if we have a state left angle, psi right angle, we can always write it as a linear combination of the computational basis states. In fact, it holds that left angle psi right angle equals the sum over x of alpha angle x right angle, where the sum is overall the computational basis states left angle x right angle and alpha n equals left angle x middle right angle. This is easy check because left angle psi right angle equals left angle x right angle, the sum over u of alpha angle a right angle e right angle equals the sum over a of alpha n right angle x middle angle equals alpha. The last identity follows from the fact that left angle x middle, the right angle is 1 if x equals I in 0. Otherwise, remember that the computational basis is an orthonormal basis. Then the expectation value of half in the state left angle psi right angle can be computed as sum over x of left angle alpha and right angle squared. And moreover, we know that left angle alpha right angle squared equals left angle x middle c right angle squared is the probability of obtaining left angle x right angle when measuring left angle pi right angle in the computational basis. In this way, the expectation value matches the statistical expected value of the measurement. Quantum approximate optimization algorithm is used to estimate the value of the cost function when running coalesced circuits in a quantum computer. These properties may seem dependent on the particular form of the Hamiltonians that we have been using. But in fact, they are very general results, and we will use them extensively in our study of the VK algorithm. But before we get to that, we will need to introduce the general notion of observable, which is precisely the topic of the next subsection. Observables. Up until this point, we have only considered measurements in the computational basis. This has worked well enough for our purposes, but in doing so, we've ignored some details about how measurements are truly understood and described in quantum mechanics. We are now going to fill that gap. We encourage you to go slowly through this section. Take your time and maybe prepare yourself a good cup of your favorite hot beverage. We encourage you to go slowly. Take your time, maybe prepare yourself a good cup of your favorite hot beverage. The ideas presented here may seem a little bit strange at first, but you will soon realize that they fit nicely with what we have been doing so far. In quantum mechanics, any physical magnitude that you can measure, also known as a physical observable, is represented by a Hermitian operator. In case you don't remember, these are linear operators that are equal to their adjoints conjugate transposes. That is, they satisfy a dagger equals A. Thanks to learn. You may remember how working with quadratic unconstrained binary optimization problems, we worked extensively with Hamiltonians. These in general are Hermitian operators that are indeed associated with an observable magnitude. The magnitude is none other than the energy of the system. The nice thing about Hermitian operators is that for them, one can always find an orthonormal basis of eigenvectors with real eigenvalues, please. Check Appendix B, Basic Linear Algebra, if you need to review these notions. This means that there exist real numbers lambda j, a equals 1, L, all of them different, and states left angle lambda angle, where j equals 1, L and k equals 1, Such that the states left, brace left angle lambda drag. Right in JavaScript, G comma K form an orthonormal basis. A left angle lambda, right angle equals left angle lambda. For every G equals 1, L, and for every K equals 1, right. Here we are considering the possibility of having several eigenvectors left angle lambda associated with the same eigenvalue lambda, hence the use of the superindices K equals 1, We'll write the number of eigenvectors associated with the lambda eigenvalue. All the eigenvalue are different. Quite common case, then we will have H equals 1 for every G. And we can simply drop the K super indices. What is the connection of these Hermitian operators with physical measurements? Let's consider an observable be represented by a Hermitian operator. And also an orthonormal basis of eigenvectors left brace left angle lambda. Right angle right brace subscript J comma K set the left angle lambda. Right angle equals lambda. Left angle lambda. This representation must be chosen to take the following into account. The possible outcomes of the measurement of the observable must be represented by the different eigenvalues, lambda. The probability that a state left angle psi right angle will, upon measurement, yield lambda must be the sum over k of left angle. Left angle lambda, 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 say right angle squared. All of this is axiomatic. It is a fact of life that any physical observable can be represented by a Hermitian operator in such a way that those requirements are satisfied. Moreover, it is a postulate of quantum mechanics that if the measurement returns the result associated to an eigenvalue lambda, the theta state of the system will then become the normalized projection of left angle psi right angle onto the space of eigenvectors with eigenvalue lambda. And this means that if we measure a state in a superposition such as a sum over j comma k of alpha gingis left angle, and we obtain a lambda as the result, then the new state will be the sum over k of alpha left angle lambda g right angle over square root of the sum over k of left angle alpha angle Quaker. This is what we call the collapse of the original state. And it is exactly the same phenomenon that we considered when studying measurements in the computational basis back in foundations of quantum computing. The word observable is often used for both physical observables and for any Hermitian operators that represent them. Thus, we may refer to a Hermitian operator itself as an observable. To avoid confusions, we will usually not omit the physical adjective when referring to physical observables. As a simple example, whenever we measure in the computational basis, we are indeed measuring some physical observable, and this physical observable can, of course, be represented by a Hermitian operator. This is, in a certain sense, the simplest observable in quantum computing, and it is natural that it arises as a particular case of this more general theory of quantum measurements. The coordinated matrix of this measurement operator with respect to the computational basis could be the diagonal matrix. I begin P matrix. Here assume backslash new line. Into a backslash new line. CT in backslash new line. CNT trying -1 backslash new line. NP matrix. Exercise 7.1. True that indeed. The previous matrix is the coordinate matrix on the computational basis of a Hermitian operator that represents a measurement in the computational basis. And we measure a single quip in the computational basis, the coordinate matrix with respect to the computational basis of the associated Hermitian operator could well be equals begin P matrix. 0 backslash new line. 0 and backslash new line. In P matrix, comma. Z equals begin P matrix. And 0 backslash new line. 0 and -1 backslash new line. In P matrix. That last matrix was the unmistakable poly-Z matrix. Both of these operators represent the same observable. They only differ in the eigenvalues that they associate to the distinct possible outcomes. The first operator associates the eigenvalues 0 and 1 to the qubits value being 0 and 1 respectively, while the second observable associates the eigenvalues 1 and 1 to these outcomes. Important note. Measurements in quantum mechanics are represented by Hermitian operators, which we refer to as observables. One possible operator corresponding to measuring a quip in the computational basis can be the poly-Z matrix. And now that we know what an observable is, we can study what its expectation value is and how it can be computed. The expectation value of any observable under a state left angle psi right angle can be defined as left brace or right brace sub psi equals the sum over j comma k of left angle lambda lambda squared lambda, which is a natural definition that agrees with the statistical expected value of the results obtained when we measure left angle psi right angle according to as intuitive as this expression may be. We can further simplify it as follows. Left angle, right angle P, right angle, a left angle psi. Right angle equals the sum over j comma k of left angle psi, middle lambda, C. Right angle lambda, sorry. Vagal lambda equals the sum over j, comma k of left angle lambda. Diagonal left angle psi. Middle lambda equals the sum over j, comma k of left angle. By left angle lambda C, right angle angle lambda chi, right angle pi, angle A. The sum over j comma k of left angle lambda A, that angle lambda, right? Angle left angle lambda check right angle equals left angle psi right angle left angle phi right angle. Notice that we have used the fact that left angle lambda lambda right angle equals lambda, like angle lambda. And the left angle p right angle equals the sum over j comma k of left angle lambda lambda lambda. Right angle left angle lambda. Right angle lambda lambda lambda. This latter identity follows from the fact that left brace left angle lambda right angle right brace subscript j comma k, it is an orthonormal basis. And in fact, it can be proved in exactly the same way we did for a computational basis at the beginning. This expression for the expectation value agrees with our previous work in quadratic unconstrained binary optimization problems. Important note, any expectation value of any Hermitian operator, observable, is a left brace or right brace sub psi equals the sum over j comma k of left angle lambda, right angle lambda squared lambda, sorry, right angle say right angle, left angle p right angle. Notice that from the very definition of the expectation value of an observable, we can easily derive the variational principle. This principle states, as you may recall with quadratic unconstrained binary optimization problems, that the smallest expectation value of an observable is always achieved at an eigenvector of that observable. And to prove it, suppose that lambda 0 is minimal among all the eigenvalues of A. Then for any state psi, it holds that left brace or right brace sub cc equals the sum over j comma k of left angle lambda lambda, left angle lambda, squared lambda, right angle squared lambda, k of left angle lambda lambda lambda, right angle squared lambda, and equals lambda 0. Where the last equality follows from the fact that the sum over j comma k of left angle lambda squared equals 1. Since the sum of the probabilities of all the outcomes must add up to 1. You now take any eigenvector left angle lambda and see right angle associated to lambda. Left angle lambda. D right angle lambda. Lambda equals lambda. Lambda. Right angles lambda. Proving that the minimum expectation value is indeed achieved at an ejector of A. Obviously, if there were several orthogonal eigenvectors associated to lambda, any normalized linear combination of them would also be a ground state of A. In this subsection, we have studied the mathematical expression for the expectation of any observable, but we don't yet know how to estimate these expectation values with quantum computers. How could we do that? Let's keep learning, because we will be exploring it in the next subsection. Estimating the expectation values of observables. In the context of the VK algorithm, we will need to estimate the expectation value of a general observable. That is, we will no longer assume that A is diagonal, as we have done. For this reason, we will need to develop a new method for estimating the expectation value of left angle p right angle left angle p right angle. We know that for a given state left angle p right angle, the expectation value of can be computed by a sum over j comma k of left angle lambda, right angle squared lambda. If we knew the eigenvalues lambda cham, the eigenvectors left angle lambda right angle right brace subscript j comma k of A, we could try to compute left angle lambda, so right angle squared, and hence the expectation value of A. However, this is information that we usually don't know. And in fact, the purpose of VK is precisely finding certain eigenvalues and eigenvectors of a Hamiltonian. Moreover, the number of eigenvectors grows exponentially with the number of qubits of our system. So even if we knew them, computing expectation values in this way might be very computationally expensive. Thus, we need to take an indirect route. For this, we will use the fact that we can always express an observable on n qubits as a linear combination of tensor products of Pauli matrices. See, for example, the famous lecture notes by John Preskill. Actually, will be, in most cases, given to us in such a form in the same way that the Hamiltonians of our combinatorial optimization problems were always expressed as sums of tensor products of Z matrices. So consider, for example, we are given an observable. N equals 1/2 Z tensor product, I tensor product, X minus 3, I tensor product, V tensor product, Y plus 2, Z tensor product, X tensor product, Z.